In the last 48 hours, the sun didn't just erupt once. It fired 3 distinct blasts of magnetic plasma directly at Earth. Right now, these storms are racing across the solar system, but they aren't going to hit us one by one. The physics of deep space is forcing them to combine into a single, supercharged wave. Here is what happens when a solar train hits our grid. To understand the sheer scale of what is heading our way, we have to look 93 million miles backward and examine exactly what just happened on the surface of our star. Right now, the sun is in the highly active phase of its 11-year cycle. If you were to look at the sun through a filtered telescope, you would see that its surface is not smooth. It is essentially a boiling, churning ocean of electrically charged gas called plasma. Plasma is the 4th state of matter. It is so incredibly hot that the electrons are literally ripped away from their atoms, creating a fluid that is highly sensitive to magnetic fields. Deep inside the sun, incredibly strong magnetic fields are constantly twisting, turning, and getting tangled up in this boiling plasma. Sometimes these magnetic field lines punch right through the surface of the sun, creating dark, cooler patches that we call sunspots. Think of these magnetic fields like incredibly thick rubber bands. As the sun rotates, these rubber bands get twisted tighter and tighter. Tension builds for days or weeks. Eventually, the star's physics demands a release. The rubber band stretches too far and it completely snaps. When that magnetic rubber band snaps, it creates an enormous explosion. If it just releases a sudden, brilliant flash of light and radiation, we call it a solar flare. A flare reaches Earth in just 8 minutes, traveling at the speed of light, but sometimes the explosion is so powerful that it physically rips a massive chunk of the sun's outer atmosphere away and hurls it out into deep space. This is called a coronal mass ejection, or a CME. I want you to imagine a CME simply as the sun burping out a giant cloud of supercharged magnetic gas and fire into space. Unlike a solar flare, which is just light, a CME is a physical heavy cloud of matter. It is made of billions of tons of actual particles. It has weight, it has density, and it carries its own internal magnetic field. Because it has physical mass, it moves much slower than light, usually taking a few days to cross the solar system. Over the last 2 days, an intensely tangled sunspot cluster rotated perfectly into the strike zone, the specific area of the sun pointing directly at the Earth. And it didn't just snap once. The magnetic tension in this specific cluster was so chaotic and complex that it snapped, retangled, snapped again, and then snapped a 3rd time. It released 3 separate coronal mass ejections within a 48-hour window. The first eruption was a moderate blast. It lifted off the surface and began its journey toward Earth at a relatively average speed of about 1 million miles per hour. About 14 hours later, the sunspot snapped again, releasing a second cloud of magnetic gas. This one was slightly hotter and moving a bit faster. Finally, on the second day, the underlying sunspot gave way entirely, releasing a third, incredibly energetic blast that shot into space much faster than the first 2. If deep space were completely empty, these 3 clouds would just travel in a straight line, completely independent of each other, and hit the Earth on 3 separate days. We would get a mild bump on Tuesday, another bump on Wednesday, and a slightly bigger bump on Thursday. Our planet deals with isolated bumps all the time, but deep space is not empty. And because it is not empty, the rules of motion completely change how these 3 storms behave. We naturally think of the space between the planets as a pure, perfect vacuum. We assume there is absolutely nothing there. But that is incorrect. The solar system is actually filled with a constant, thin stream of particles blowing off the sun in every direction. This is called the background solar wind. It is like a very thin, invisible fluid that fills up the entire space between us and the sun. Because space is filled with this fluid, a coronal mass ejection experiences friction. When the first solar burp leaves the sun, it has to push its way through this background solar wind. It is plowing through the invisible fluid, which creates drag. That drag actively pulls on the storm, fighting its forward momentum and slowing it down. To understand exactly how this works, imagine a major highway in the middle of winter, completely covered in 10 feet of heavy, wet snow. If you send a single snowplow out to clear that highway, the truck has to work incredibly hard. The engine is roaring, the tires are slipping, and the heavy snow creates immense resistance. The plow is moving forward, but it is moving slowly because it is doing all the heavy lifting to physically clear the path. That is our first CME. The first blast is the heavy snowplow. It is taking the brunt of the friction, pushing the background solar wind out of the way, and slowly carving a wide, clear tunnel through the inner solar system. Now imagine sending a second and a third snowplow down that exact same highway an hour later. These trailing trucks do not have to push through any snow. The road in front of them is perfectly clear, smooth, and frictionless. Because there is no resistance, these trailing trucks can hit the gas and accelerate to their absolute top speed. It is the exact same concept as a race car drafting behind the leader on a track to conserve energy and gain speed. This is the exact fluid dynamic playing out 93 million miles away right now. The first CME cleared the tunnel. The second and third CMEs, which were already launched at faster speeds by the sun, are now traveling through a frictionless vacuum left behind by the first storm. They are experiencing absolutely zero drag. Because of this, they are accelerating, rapidly closing the gap between themselves and the heavy plow in front of them. They are moving too fast. The highway is too short. When the physics of speed dictate that these three separate storms are going to physically collide before they ever reach our planet. When the fast train catches up to the slow train, it doesn't cause a mechanical crash like vehicles on a highway. Remember, these are vast clouds of superheated, electrically charged gas. When they meet, they merge. Space weather forecasters have a very specific, highly descriptive term for this phenomenon. They call it a cannibal CME. The faster, trailing solar storm literally cannibalizes the slower storm in front of it. It sweeps it up, eats it, and completely absorbs its matter. But this is no mere addition. When you combine 1 billion tons of plasma with another billion tons of plasma, you do not just get a larger cloud. You get a vastly more complex, highly energized structure. Every CME carries its own internal magnetic field, those twisted rubber bands we talked about earlier. When 2 or 3 CMEs merge in deep space, their magnetic fields crash into each other. Sometimes they repel, but often they tangle together in a volatile process called magnetic reconnection. This process can physically alter the shape of the storm. Instead of a soft, billowing cloud, the front edge of the cannibal CME becomes incredibly compressed. It forms a sharp, hard magnetic shockwave. It acts like a supersonic wall of electricity rolling through space. Historically, cannibal storms are responsible for some of the most intense space weather events ever recorded on Earth. During the famous Halloween storms of 2003, a series of back-to-back solar eruptions merged in transit. When that combined wall of plasma hit the Earth, the resulting magnetic disturbance was so strong that it forced air traffic controllers to reroute commercial flights away from the polar regions, when it caused a widespread power blackout across parts of Sweden. Up in orbit, the radiation levels spiked so intensely that the astronauts living aboard the International Space Station had to immediately abandon their normal duties and take shelter in the heavily shielded Russian Zvezda module to protect their DNA from being damaged. The complexity of a cannibal storm is what makes it so incredibly difficult to forecast. When forecasters at the Space Weather Prediction Center look at a single CME, they can easily calculate its speed, its density, and its arrival time. But when 3 storms merge, the mathematics become deeply chaotic. We do not know exactly how those 3 distinct magnetic fields will interact when they combine. We do not know if they will cancel each other out, or if they will perfectly align to create a supercharged, high-density shockwave. What we do know is that a massive, combined wall of magnetic gas is currently hurtling toward us, and standing in its way is a single, invisible shield. The Earth is not entirely defenseless against a solar train. If we didn't have a planetary defense system, these rolling waves of superheated plasma would have stripped away our atmosphere billions of years ago, leaving our planet looking exactly like the dry, barren surface of Mars. Our defense system is called the magnetosphere, and it is generated deep beneath your feet. About 2,000 miles below the Earth's crust lies the outer core. It is a massive ocean of liquid iron and nickel, heated to thousands of degrees. As the Earth spins, this liquid metal churns and flows, acting like an enormous planetary dynamo. This movement of liquid iron generates a powerful magnetic field that extends far out into space, wrapping the entire planet in an invisible protective bubble. This bubble is not a perfect sphere. The side facing the sun is pushed inward by the normal, everyday solar wind. The side facing away from the sun is stretched out into a long, trailing tail, much like the wake of a boat or the tail of a comet. Under normal conditions, when a standard solar burp hits this bubble, the magnetic shield easily deflects it. The charged gas simply slides around the edges of our bubble, harmlessly washing past the Earth and continuing out into deep space. But a cannibal CME changes the math. When a combined, dense shockwave of plasma slams into the Earth, it does not just wash over us. The physical weight and extreme magnetic force of the storm actively push against our shield. Imagine taking a soft foam stress ball in your hand and squeezing it as hard as you can. The foam compresses. That is exactly what happens to our magnetic field. The front edge of the bubble, which normally sits about 40,000 miles away from the surface, gets violently compressed. Under the weight of a heavy solar train, that boundary can be squished down to 20,000 miles or even less. When the shield gets squished this much, it exposes the highest layers of our orbit. Critical communication and weather satellites that normally float safely inside the protective bubble suddenly find themselves outside the shield. They are temporarily exposed to the raw, unfiltered radiation of deep space, which can scramble their electronics, inject false commands into their computers, or physically degrade their solar panels. But the real drama happens on Earth's night side. As the dense plasma wave washes around the compressed front of the bubble, it drags along the trailing magnetic tail. It stretches that tail longer and tighter, pulling the magnetic rubber bands of the Earth to their absolute physical limit. Eventually, the tail tension breaks. The magnetic lines snap and reconnect, slingshotting millions of tons of trapped, energized particles straight down the magnetic field lines into the Earth's upper atmosphere, specifically targeting the north and south poles. When these energetic particles hit gas in our atmosphere, they light up. The physics here is exactly like a neon sign in a storefront window. In a neon sign, electricity runs through a glass tube filled with gas, exciting the gas and making it glow. When the space electricity hits our atmosphere, it excites the natural gases. If the particles hit oxygen high up, they glow a brilliant red. If they hit oxygen lower down, they glow green. If they hit nitrogen, they emit stunning blues and purples. This is the aurora borealis, or the northern lights. Usually this light show is confined to places like Alaska, Canada, and Scandinavia. But when a cannibal CME heavily compresses the shield, the auroral oval expands rapidly. The lights are pushed far south. During a major event, you can walk outside in places like Texas, Arizona, or even Florida, look up, and see the sky burning with glowing red and green ribbons of light. It is a stunning, beautiful visual display. The glowing sky is just the visible evidence of an invisible, highly disruptive electrical transfer taking place all around us. While the public looks up to photograph the northern lights, grid operators and engineers are looking down. They are focused on the dirt beneath our feet and the wires hanging over our heads. To understand why a space storm breaks machines on the ground, we have to talk about a basic law of physics called electromagnetic induction. In the 1800s, a scientist named Michael Faraday discovered that if you take a magnet and wave it back and forth over a copper wire, it creates an electrical current inside that wire. Moving magnetic fields naturally generate electricity. When a cannibal CME squishes and shakes the Earth's entire magnetic field, it is essentially waving a giant planetary-sized magnet over the ground. This creates deep, unwanted electrical currents pulsing straight through the Earth's crust. We call these geomagnetically induced currents, or GEICs. We actually saw exactly how dangerous these ground currents can be long before the modern power grid existed. In September of 1859, the Earth was hit by the most powerful solar storm in recorded history, an event known as the Carrington event. Back then, we didn't have cell phones or power lines, but we did have the telegraph system. When the massive magnetic shock wave hit the Earth in 1859, it induced so much electricity into the ground that it climbed up the grounding wires of the telegraph poles. Telegraph operators received severe physical electrical shocks through their equipment. The extra voltage was so intense that the telegraph paper literally caught fire. In some cases, operators realized they could disconnect their heavy batteries and continue sending messages using nothing but the ambient electrical current flowing straight out of the sky. We do not have to look back to the 1800s to see the devastating reality of these ground currents. In March of 1989, a severe solar storm slammed into the Earth and directly targeted the magnetic vulnerabilities of North America. When the space-generated electricity surged through the bedrock of eastern Canada, it found the massive transmission lines of the Hydro-Quebec power grid. The result was not a slow, gradual failure. The extreme voltage fluctuations tripped critical protective relays across the entire network in a terrifying cascade. In exactly 92 seconds, the entire power grid of the Canadian province completely collapsed. 6 million people were instantly plunged into absolute darkness during the freezing temperatures of a harsh Canadian winter. Traffic lights died, airports shut down, and subways stalled in underground tunnels. It was a stark, 92-second lesson in how incredibly fragile our modern electrical lifelines actually are. Today, our civilization is vastly more vulnerable. Electricity is lazy. It always wants to find the absolute easiest path to travel. Dirt and rock are highly resistant to electricity. But humans have spent the last 100 years wrapping the planet in millions of miles of thick, highly conductive copper and aluminum wire. When this space-generated electricity flows through the ground today, it naturally seeks out our long-distance, high-voltage transmission lines. It climbs up the grounding wires and injects itself directly into the power grid. This is a massive problem because the grid is not designed to handle it. Our power grid operates on alternating current, which means the electricity pulses back and forth exactly 60 times a second. But the unwanted electricity generated by the solar storm acts like direct current, a solid unmoving wall of electricity. The absolute weakest link in the entire grid is the step-up transformer. These are the giant, incredibly expensive, oil-filled metal boxes sitting at power substations. Their job is to take electricity from a power plant and step the voltage up so it can travel hundreds of miles across the country. When the solid wall of space electricity hits a transformer, it completely saturates the heavy magnetic core inside the metal box. The transformer becomes confused. It stops working efficiently and starts converting the electrical energy directly into intense, radiating heat. If the solar storm is strong enough and the current lasts long enough, the copper coils inside the transformer literally begin to melt. The insulating paper wrapping the coils carbonizes. The transformer violently fails. But replacing one of these step-up transformers is not like swapping out a blown fuse in your basement. These are incredibly massive, custom-built pieces of industrial hardware. A single high-voltage transformer weighs hundreds of tons. They cannot be mass-produced, and they take anywhere from 12 to 24 months to manufacture and transport on highly specialized, multi-axle heavy-duty train cars. We simply do not have a massive warehouse sitting somewhere full of backup transformers. If a cannibal CME melts down dozens or hundreds of these transformers simultaneously across multiple states, restoring power to a major city would not take days. Parts of the continent could remain completely dark for months, plunging society into an unprecedented logistical nightmare. And this invisible electrical threat does not just hunt for power lines hanging in the sky. It also hunts massive steel arteries buried deep underground. Millions of miles of steel pipelines carrying critical crude oil, natural gas, and refined fuel crisscross the United States. Just like the copper wires on the grid, these long, continuous metal pipes act as giant conductors for geomagnetically induced currents. When the space electricity enters a pipeline, it violently accelerates the natural process of electrochemical corrosion, silently eating away at the structural integrity of the steel. Worse, the stray voltage aggressively interferes with the delicate, automated electronic pressure control valves that regulate the flow of the fuel. A strong enough surge can cause these valves to malfunction, either shutting down the fuel supply entirely or creating dangerous, uncontrolled pressure spikes within the underground network. The solar train is not a cinematic disaster that blows up buildings. It is a deeply mechanical threat that hunts for the specific vulnerabilities in our heavily connected, highly synchronized infrastructure. So, what is the exact timeline, and how much warning will we actually get before this wave hits the grid? Space is vast. Even moving at over 1 million miles per hour, a coronal mass ejection takes roughly 2 to 3 days to cross the 93 million mile gap between the Sun and the Earth. Because the initial eruptions happened over the last 48 hours, the arrival window is opening right now. But we are not flying entirely blind. About 1 million miles upstream from Earth, sitting perfectly between us and the Sun, is a gravitational parking spot known as the Lagrange 1 point. We have placed highly specialized space weather satellites, like Disco VR, in this exact location. The gravity of the Earth and the Sun perfectly balance out at this spot, allowing the satellite to just hover there permanently. These satellites act as our deep space tsunami buoys. They sit there in the dark, waiting for the wave. When the cannibal CME washes over these satellites, they immediately register the exact speed, density, and magnetic orientation of the storm. They beam that data back to forecasters at the Space Weather Prediction Center at the speed of light. Because the storm is moving much slower than the speed of light, this gives humanity exactly 15 to 45 minutes of absolute, concrete warning before the shockwave physically slams into the Earth's magnetic shield. 45 minutes is not enough time to build new infrastructure, but it is exactly enough time for the people sitting in sterile, windowless control rooms to fight back. When that extreme warning flashes on their screens, grid operators across the country execute emergency, ticking clock defense protocols. They immediately shed excess electrical load, cutting power to large, non-essential industrial facilities to give the grid breathing room. They intentionally lower the transmission voltages across the entire network, creating a massive electrical buffer against the incoming space surge. And in a worst-case, red alert scenario, they will physically open the massive high-voltage circuit breakers to completely isolate those highly vulnerable, multi-million-dollar transformers. This aggressive strategy intentionally causes a temporary, localized blackout. By taking the grid offline manually, they save the irreplaceable hardware from melting, ensuring that once the solar storm passes, they can simply flip the switch and turn modern civilization back on. A solar train is a stark reminder that the Earth does not exist in a protective vacuum. We are floating in a highly active, deeply connected stellar environment. The sun dictates the weather in space, and our modern civilization is entirely dependent on our ability to weather the storm. Keep an eye on the sky tonight for auroras, do not panic if the power grid fluctuates, and respect the heavy physics of our solar system. If you want to stay ahead of the next major space weather event and understand the science driving our grid, make sure to hit the subscribe button below. We will keep tracking the data, and we will see you in the next briefing.